If you like that. Okay, so we gotta do systems design prep. Why am I doing this? I have a systems design interview coming up, but mainly it was one company I really wanted to work at. I messed up an interview because like he just wanted to meet with one of their new team members. I had done systems design in a minute, so I wasn't that good on it, but it's alright. What we want to do is we want to first say, ask ChatGPT, give me a table of contents, all the major system design topics. Okay. All right, and I guess our plan will be, damn, bro, they're still going? Okay, limit it to what's typically asked in a interview. Damn, this is a question I messed up. Designing a URL shortener. I didn't mess it up, but it wasn't that good. Alright, but at least we got a good idea. We're gonna watch this video on designing a distributed messaging queue.
As for non-functional requirements, we want our system to be scalable and handle load.
Because this channel is the best. He has 7 videos. You just watch it.
Increase,
it's pretty simple.
highly available, and tolerate hardware and network failures.
But messaging queue, you want to send messages between people. So think of like Facebook Messenger.
So the biggest requirements. We can be asked to support create and delete queue APIs or delete message API. There can be also respond quite local possible requirements. Interview is your friend and will help to solve the problem.
You can usually just look at the pictures, but I've watched this before, so a long time ago, but I have a good memory.
Now, let's start drafting this architecture. Let's start with components that are common for many distributed systems. Fourth, we need a virtual IP. Before the symbolic hostname, for example, myWebService.domain.com, that resolves to a load balancer system. So next, we have a load balancer. A load balancer is a device that browses client requests across a number of servers. Next, we have a front-end web service. Next.domain.com, that resolves to a load balancer system. So next is the like part with main use cases. Now, let's
update the captions. Boom, boom. Yeah, captions look really weird. How do you update these? Options, subtitles, options. Let's be like, that's good. Let's make it background color. Black is fine. Oh, that's the problem. Honestly, increase the font opacity. Boom, 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 boom. All right.
There can be also requirements for the producer. For example, system needs to avoid duplicate submissions or security requirements, or when asked to implement a specific ordering guarantees. As for non-functional requirements, the interviewer may define specific service level agreement numbers, so-called SLA. For example, effectiveness. For example, system needs to minimize. Let's start with components that are common for many distributed systems. Fourth, we need a virtual IP. VIP refers to the symbolic host name. For example.
Yeah, YouTube captions kind of suck, man. Because they're like not. I don't know. They just kind of suck. TikTok and CapCut have much better captions when you're making videos. I feel like honestly, a good Chrome extension you can make is something that can take the transcript of the audio and the clip sections and make like those live TikTok captions that show up as a person is speaking, because it's more accurate. And this one there's a delay every time the captions show up. But if I was like student working right now, I think that'd be a sick project to make, and you could just overlay it on top of the video.
myWebService.domain.com, that resolves to a load balancer system. So next, we have a load balancer. A load balancer is a device that browses client. But we need to start with components that are common for many distributed systems. Fourth, we need a virtual IP. VIP refers to the symbolic host name. For example, myWebService.domain.com, that resolves to a load balancer system. So next.
Virtual IP address.
We have a load balancer. A load balancer is a device that routes client requests across a number of servers. Next, we have a front-end web service, a component responsible for initial request processing, like validation, authentication, etc. Queue metadata, information like its name, creation date and time, owner, and any other configuration settings, will be stored in a database. And best practices dictate that databases should be hidden behind some facade, a dedicated web service responsible for handling calls to a database. And we need a place to store queue messages. So let's introduce the database in a creation date and time. Queue metadata, information like its name, creation date and time, owner, and any other configuration settings, will be stored in a database. And best practices dictate that databases should be hidden behind some facade, a dedicated web service responsible for handling calls to a database.
Okay, so I think this is our first major principle. Always hide a database behind a service that interacts with it. So that just means an API. You don't want to have whatever program you're doing hitting the database directly. You just want a level of abstraction there. So this person sends a message, this person receives a message. Virtual IP. Yeah, I know what IP addresses are, but what's the point of a virtual IP? That's why we have ChatGPT. Virtual IP in systems design. Virtual IP, high availability. Load balancing. Was virtual IP goes to a load balancer? Okay, so yeah, I guess it's just something you use for routing in the load balancer. So it sends to a virtual IP, which sends to, it's not a single load balancer. Usually, like, everything in distributed systems is like, oh, one load balancer fails, now you need more load balancers. But you could just say it's a single one, just for simplicity. Because this is not, it's like a afterthought. Like, you're not going to scale up everything. You're going to talk about the main design and then how to scale it up. Like, oh yeah, you might have to scale up load balancers, but there's services to that for you. Should we know the service's name? Like Kubernetes, when one load balancer goes down, replace it. So you're never actually like interacting with these components by yourself. Like most of the time, like there's always some database that will have some trade-off between the cap theorem. So you don't really have to implement it yourself. That'd be a cool project though, implementing your own load balancer. You should take a distributed systems class, because I think that's where I learned the most about distributed systems, because they like really break it down. And networks. Networks is also one of my favorite classes. So this front end thing here is probably like the
configuration settings will be stored in a database. And best practices dictate that databases should be hidden behind.
Yeah, so database hitting beside some facade. That metadata service is just the API you're hitting. So metadata. And that just holds information about who's sending the messages. So in case you were wondering what metadata service is, or metadata DB is.
And we need a place to store queue messages. So let's introduce a backend web service that will be responsible for message persistence and processing. Now, let's take a look at each component one by one. Load balancing is a big topic, and unless interviewer encourages you to dive deep into load balancing topic, we better not deviate too much from the main question of the interview.
Yeah.
Always try to stay focused on what really matters. Internals of how load balancers work may not matter, but in order to make sure non-functional requirements to the system we built are fully met, we need to explain how load balancers help us achieve high throughput and availability. When domain name is hit, a request is transferred to one of the VIPs registered in domain name system for our domain name. A request is transferred and availability. When domain name is hit, a request is transferred to one of the VIPs registered in domain. name system for our domain name. VIP is resolved to a load balancer device, which has a knowledge of front-end host. By looking at this architecture, several questions have probably popped in your head. First, load balancer seems like a simple single point of failure. What happens if load balancer device goes down? Second, load balancers have limits with regard to number of requests they can process and number of bytes they can transfer. What happens when our distributed message queue service becomes so popular that load balancer limits are reached? To address high availability concerns, load balancers utilize a concept of primary and secondary nodes. The primary node accepts connections and serves requests, while the secondary node monitors the primary. If for any reason the primary node is unable to accept connections, the secondary node takes over. As for scalability concerns, the concept of multiple VIPs, sometimes referred as VIP partitioning, can be utilized.
Okay, so VIP partitioning is just figuring out how to split up the request. So you assign a virtual IP address, and that will assign it to a different load balancer, I'm guessing.
In DNS.
And then load balancer is another level of abstraction where we assign it to different front-end hosts. So there's two levels of splitting up the requests coming in because we want high throughput. So we want like a lot of requests to be able to be handled in a fast way. So we can't just have one service. We got to scale all of our services. So we go from your request, make a virtual IP for it, and then that will send it to its appropriate load balancer. And then that load balancer will send it to its appropriate front-end service.
We assign multiple area cards to the same DNS name for the service. As a result, before as V partitioning can be utilized.
So that's called V partitioning? Or VIP partitioning?
In DNS, we assign multiple area cards to the same DNS name for the service.
Okay.
As a result, requests are partitioned across several load balancers.
Yeah.
And by spreading load balancers across several data centers, we improve both availability.
Oh, and then you do different data centers because if one data center goes down, you have other data centers. So data centers, you probably have them in different locations. Like if you go on Firebase, there's like US West, US East, and it's like in different, basically data centers across the US. But it's also due to you want data centers in places where you have a lot of users, so there's less like delay when sending a request and then getting it back. Like in Europe, you'd probably, if you have a ton of users, you probably have a data center in Europe that they're hitting, just because now they don't have to make the request that goes all the way to US to get the information and then all the way back. Like people don't think distance matters, but apparently it does because they do that. And if you have multiple data centers, say the Europe one is down, it can instead route it to, the load balancer could route it to the, American data center. And it'll still have
and
information.
Performance. Let's move on to service. And authorization.
Okay, lightweight web service.
Rate limitation.
Oh, okay, so this is the point. You gotta do what each service says. First, front-end service. Validate the request. Authentication, check if they're logged in, authorize it, check if they can make this, server-side encryption, encrypt their message, cache messages that came in, rate limit, avoid spamming, request dispatching, and request deduplication. So sometimes you hit multiple times. So there's at least once, at most once, or exactly once. Okay, so this is me going back into like what I learned in university. If we start this, there's the at least once, at most once, and exactly once. So when you send a request, actually my bad. Request, you have three options. At least once, at most once, or exactly once. This one is what most people opt for. Add deduplication somewhere in system to avoid processing the same request. So what does this do? This is actually, let's see, there we go. And then what is this? Trade-off of sending more requests, but benefit of what do you see? The benefit is it's a likely benefit of robustness handle requests, no, handle failures better, because you're sending multiple, handles failures better. But there's like more additional there's additional logic that you have to add for this, which is just the deduplication. At most ones, this one is not very robust, simple to implement. Actually, it's not that. At most ones, not very robust, but reduces the load on the system exactly once. This is idealistic because it assumes there's going to be no issues with what do you call it? Assumes there are going to be no issues with request handling. So like there's not going to be any node failures. It's not going to be corrupted in some way. But we could just ask ChatGPT to explain the process of at most once, exactly once, and at least once. Blah blah blah. System simply delivery semantics. No more than once. Pros, there's no duplicates, less overhead, but you're probably gonna lose the message. It's reliability, not robustness. So the message is more likely to be delivered because you have retries. Duplicate handling, more overhead, exactly once, no duplicate, no message loss. Ideal for critical applications, but this is like very, very unlikely to work out just because systems do fail, and that's why it says complexity. Careful tracking of the message delivery and deduplication, additional performance overhead, and potential latency. So most people would want 3, but they opt for 1 because deduplication is simple to implement. You just keep like a set of commands that you've already responded to, so you can avoid having to respond to it again. So this one, exactly once, AML 1, ALO. Yeah, basically. They'll never ask you anything too low level, because whenever we were doing our systems design or distributed systems course, we would go on to like transactions and how they're made of read and writes. So transactions are atomic or acid compliant, and I guess you guys should know what an acid is. It's atomic, consistent, idiomatic, I don't know. And actually, let's see what the atom one. Atom distributed systems. Atomic commit protocol. Oh wait, no, not atom, acid. Okay, atomic, consistent, isolation, durability. That's what it was. Okay, so what is acid compliant? This is more for databases, but we were doing this on a low level with like transactions and how they're consistent of read and writes, and different like write ahead cache was a concept we learned. So how we could reverse transactions when they're already starting to be committed. So if you have to do computer science, because I know there's one guy, Coding Jesus, who like he basically roasts people because they don't know like simple things like what's TCP. And since he's a C++ developer, he like grills people on like pointers and like, oh, what is this value? What is a TOML file? What is a wheel file if you're a Python developer? But he's kind of right in a sense. Like you can get into your niche and you wouldn't have to like really delve into these things, but is it good to know? Absolutely. You know, it's always good to know things to level up. But it grills people, and a lot of it is networks. So networks is knowing like how computers work from the ground up. And the second one he grills people on is... Wait. This is... Okay. OBS fails me. Wait, I gotta make sure the stream is even working. One sec. Okay, it's working. Sweet. Okay, so he grills people on networks and distributed systems. So if there's two courses you take these two. These were optional courses, but I took them both because they're just extremely important to know. So atomic, all transactions are treated as a single unit. What does this mean? So a transaction is just a series of read and writes. So that means if some read or / write fails, like that's like a deadlock example, or there's some, deadlocks are a good example. Then what do we have to do? We have to reverse that transaction. So if you don't know what a deadlock is, it's basically when two resources try to access the same thing, but create a situation where neither can access it. So transaction A, let's see, reads value B, which is A, updates value B, but at the same time, transaction B updates values of B. But then we have two updates, but transaction A holds an old value of B.
Who are you talking to?
Dude, I'm talking to myself, man.
Oh.
Yo, that's how you learn. You gotta pretend you're teaching somebody.
Are you doing like systems design actual questions?
Yeah, because I did the distributed systems course. Dude, all of it is distributed systems. I'm just trying to like get ready for my one interview. And then, I'm so mad I messed up Credo. That was like,
That was an easy one, man. You should be mad.
Dude. If you don't know how, do you know what I was saying? I was saying stuff about like DNS, and I was like, I was talking about networks.
If you know it, you know it. If you don't,
if you know it, you know it. If you don't, you don't. But
I remember they actually like the top K one. I'm like, he's a heap, man. I don't know what else to say. Like,
it's like a count hash map. It's this really weird hash map.
I'm not gonna know that. I'm not gonna think of a count hash map. I don't know what that is.
It's like a very special data structure that approximately gets the value right. And
that's
like,
so dumb.
What do you mean? But
one time I was explaining something. So we need some kind of like a order, and then we have like a little DB here that checks if the jobs are being scheduled and finished. And I was explaining the entire system. The guy's like, so like a queue, and I'm like, there it is.
That's what I want.
That's a good way to kind of wrap up what I'm trying to explain.
First in, first out, something that would maintain that ordering. Maybe some type of
we need to
list.
retry the jobs that fail, and then you send the jobs in, and then it comes out.
Yeah, man.
That was my credo interview.
Dude, my credo interview, he's like, make a URL shortener. And I was like, okay, so the DNS, it works with the A name and the IP address. And then I started talking about that. And then I'm like, wait a second. A website has multiple IP addresses based on the location.
I'm still waiting for the Snapchat guys to get back to that.
Wait, this is live. It's live. It's fine.
That's okay, no one's listening. No one's listening.
No, wait, I did have 3 viewers. I did have 3
him
viewers.
Like 6 times, and then he got back to me.
My viewers,
like,
where are you? Comment.
Whatever, huh?
Dude, it's tough, man. I just want to work for that. I don't know, just a cool startup, but yo, man.
I want to work at a nice big company.
You know, this is like a. Don't say that. What if they watch?
No, I want to learn. I feel like at a startup, they're gonna work me too hard. I'm not gonna learn as much. I want to learn good systems and good design principles.
Dude, I feel like you get like if you don't build it from 0 to 1, you don't really learn it.
I think it's good to learn like.
Dude, here's a rant.
Coding.
So many YC companies, they make you do a take home, and they say, "Oh, it's only 4 hours," and you're like, "I don't know Python. I don't know how to do this. It's not taking me 4 hours."
How Anthony was like, "Oh, if you guys want any W24 jobs, like
Winter 24 from YC.
Yeah, he's like, just let me know."
Bro, okay. I'm like thinking about it. I'm like, yo, some of these YC companies, I don't want to work for.
I literally see there's like a full on-site, all these interviews,
and they're like,
after that, they're like, "Come work with us for 2 weeks."
Dude, somebody in YC has been telling people to give everybody 4 hours take homes that realistically take 8 hours because you don't know their staff.
Don't do the. We're talking about. You do the voice.
I'm doing the voice. I'm telling the people. They give you a 4-hour take home. Hey, it realistically takes you 8 because
who's that?
We don't know the stack.
Hey guys, my name is Baxter, and if you're not gonna do this, you'll never.
Dude, don't say that. Don't say that. He might be watching one day.
I hate that guy.
Don't say that. Baxter Carter is a great guy.
My friend made $3 million ads, and if you don't do this, you'll never make it.
This is live.
He's so obnoxious. I hate that guy.
Hey, it's okay. But they do the take homes, and then do you know what's the worst one? The 2-day on-site. I'm like, bro, I'm not working with you guys for 2 days for you. You say, you didn't really mesh with the team well, and I'm like,
I'll be on the outside. Here's some guys. How's it going, everybody?
Like, people are so scared to hire. What happened to the? Oh, you graduated? Let me look at your resume. Let me talk to you for 30 minutes. All right, Bill, boy, you got a job. Like, what happened to companies taking risks? I thought that was what startups were about, man. Taking risks.
You know that guy, Brian Chesky. He ruined it for everyone. The Airbnb douchebag. He was like, "Oh, if you're gonna die in 1 year, would you still work at Airbnb?"
No.
Like, what? Like, everyone was lying on that interview. Yeah. And then he waited 5 months to hire his first guy, and he's like, now people hail him as a genius.
Yeah.
What
is it called? Like the survivorship bias?
Yeah.
This is survivorship bias.
Not every, like, AI ChatGPT rapper startup thinks they're Brian Chesky, and they need to give the most rigorous, like, you're just finding the most desperate engineers. You're not finding the best engineers. You're finding the guys that work.
Don't say that. That's me.
No, you're finding the guys that look any boot and do whatever you tell them. Jump through any boot. The good engineers are gonna look at that and be like, "It's not worth my time. It's good to shit."
Dude, honestly, I would do that, but some of these
maybe
companies.
That's what they want. They don't want good engineers. They want desperate engineers.
Well, dude, maybe.
Ready to jump when they say jump. Hey, we need you to work all weekend at night, unpaid. You're on salary, buddy. Okay, guys.
Do you know what's the worst part? They have at-will employment. So, do you know Abdul? He was saying to me, he's like, "Yo, check what rounds of funding they're in. Check how much money they have coming in." He's like, "Because as soon as they don't, they'll fire you."
Yeah.
And do you know what was the one YC company having AI? Yeah. Out of the 150 people I interviewed, I hired one. I asked him, I'm like, "Do you do 150 50-minute interviews?" He's like, "Yes, I did." And then he's like, "It was longer than that though, because we had second rounds, on-sites, recruiter calls, or was it HR, like team calls?" And I was like, "Bro, shut up, man. I will not do your
I've got all these first years who create an AI rapper. They got them too hyped.
I hate it.
I'm gonna create an AI rapper. I'm gonna get funding.
I don't want to get funding. I feel like then you're a punk.
Yeah, then you're like, "Please, investors, please
give me my next round of funding.
I need to make Series B.
Yeah, so ChatGPT just released AI agents, and that makes my startup invalid, but please." Do you know one company? One of the guys I was talking to, he's like, "Yeah, we were trying to make an AI for like financial stuff."
Yeah.
I'm like, "You're working on it for a year. You're head of engineering. What happened?" He's like, "We didn't make any money. We just liquidated." And I was like, "Yeah, that sounds like the story of most of these AI companies."
Wow.
But now he's working at Credo, so pretty successful.
I guess so. Oh, the Richard guy?
Yeah. Hey, don't name drop. Don't name his government.
That's pretty. I don't know. It's nothing that serious.
Yeah, honestly, if this interview thing gets too annoying, I think I'm just gonna make an AI startup. Apply to A16Z. What was the meme? Yeah, just finesse A16Z from 3 million with that AI note-taking app.
I'm gonna go message Mark Cuban and be like, "Hey man, give me some funding." I gotta take it from a billionaire. I don't want to take it from someone I know, like a niece's cousin.
Yeah.
Then I
do you know that video I sent you about they made like a device that records you 24/7, or you can record it?
Yeah. So
why can't you just use an Apple Watch?
You could use an Apple Watch. You could use your phone, press record.
Oh, but this one you could just click and nobody will know.
No, it doesn't interfere with.
You can't just make an app that streams to like a.
You know why they said it? They're like, does it interfere with any of your other phone stuff? And I'm like, that doesn't make sense. Now you gotta carry.
It's on your phone. You gotta go on your phone to look at the conversation. Do you know what we should make? We should just make an app that basically just does that. You click record and it streams it somewhere, because like uploading big files is the main problem. But if you're streaming it even from Apple Watch, I think it's pretty easy. Why are these people making devices out of it? Like the stupid people who make the necklace for AI? That's also dumb.
I don't even see the big deal. Like, I guess it's like okay app, but it's so easy to make. It's just recording, and then you put it in a vector database and search it. That's all it is. Or you don't even do that. You probably just have it ChatGPT over it.
You put it in DeepGram, get the transcription.
Put some AstroDB database.
Bro, literally all these companies, we use DeepGram for transcriptions, 11 Labs for our voices. We just use whatever models available for like the actual like, hard stuff. These guys are just making rapper companies, man.
Yeah, I remember working at Podcast AI like 2 years ago, and I was like, "How do you do the AI stuff?" And he's like, "No, we just use
you gotta make prompts, man."
And I'm like, "So you guys don't do anything?" And he's like, "No, we prompt it." I'm like, "Wow, that's cool."
I feel like everybody's just using this black box, and then every time there's a new box, they just update.
China released one. It's apparently pretty good.
Yeah, but somebody was criticizing it. He's like, "Yo, realistically, you're not gonna, even if it's open source, you're not gonna run it yourself. And do you want your information going to China?"
Yeah.
I don't care either, but that's why a lot of people, companies wouldn't use it.
Yeah, I guess so. I think I want to start a physical like store.
Dude, I think I just want to get into construction. You know,
Yeah,
something real, bro. Something real. Not any of this garbage. This is garbage.
All the software we're building, I don't think.
What was it? One company? Okay, we're gonna automate call centers. A lot of people are gonna lose their
job. You wanna
job.
follow my new Instagram channel?
What?
I was thinking, I'm so lazy, I can't start an Instagram channel, so I'm starting the most low. You see that guy that does like the day one of Novab, and it's just a back screen with his text, and he's like, "Guys, I failed." I'm doing.
There's a female version of that.
Femcel?
It was Femcel, but she was like, yeah, this guy totally into me. I can tell. It's just a parody of the cats. Yeah, day 13. Something must be working. I could tell by the aura. I was like, yo, shut up. There's like no figure. I was like, that's disgusting. That's disgusting.
Too graphic.
Yeah.
I know I'm doing that for my 10K steps. I'm gonna log my weights, how I feel.
Yeah.
Do that
I think the real thing move now is become an influencer.
Yeah, I think that's literally the biggest move. But I don't want to sell my life.
I'll sell mine.
That's my biggest thing. I don't want. You know what I was worried about? It's not even people I know. It's people I don't know going through and pretending like they know me through my videos. I don't want that happening.
You don't want somebody going up to you, yo, what's up, man? You reading
Yeah,
something?
I heard that story you told. That's crazy, man. I'm like,
I don't know you, man. Step down a little, bro.
I'll be the type of celebrity to like hate my fans. Be like, yo, what do you want?
Yo, man. Yeah,
You
no,
don't
I
know me.
No, I cannot get you a job. No, I will not review your resume. $20. It's shit.
I'm gonna go do all of the
I do review people's resumes
medium, top interview questions
for free. Yeah.
Do all the easy and medium top interview questions.
Yeah.
I'm gonna go to sleep.
I'm gonna continue talking about systems design.
Get some meat, like some kebabs or some chicken.
Yeah. Nah, man, just starve tonight. You're unemployed. that's your punishment.
I'm happily unemployed.
Yeah, me too. What's Mama saying? Anji.
Yeah.
Okay, whatever. Alright. Hopefully none of my recruiters see that. Yeah, nobody's watching. Nobody's watching. Oh, bum, 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 bum. Okay, so this is an example of a deadlock. We could just validate it with ChatGPT, but everything's a black box. It's so dystopian. Look at me, I'm talking to myself. I'm not even reading chat. Nobody's here. But believe it or not, it's a good way. What would we say, rights? So this is like probably the simplest example of a deadlock. They both read it, but one writes it. So value B, and it like adds 5. This one like adds 8. And this is a deadlock because they both try and read and write at the same time. Oh, race condition. Okay, so this is a race condition, not a deadlock. A deadlock is like when they can't access it. So, okay, I got the two mixed up. Okay, deadlock is... What is deadlock? Deadlock is like... Oh, okay. So basically you have to acquire resources, right? Transaction A acquires value B. So unless transaction A lets go of value B, then you can read to it again. Transaction B acquires value A. All right, let's say X and Y. X, Y. Transaction A tries to acquire Y. Okay, so now I'm remembering it correctly. So this is about acquiring values. This is a race condition, and race conditions lead to the idea of deadlocks, where each transaction has to acquire values, and until that transaction is completed, it will release the value and say, hey, you can read and edit this value. So then transaction A tries to acquire B. Now, this is perfectly fine because this will be waiting until B releases Y, which is transaction B. And now, say transaction B tries to acquire X. This is waiting until transaction A releases X. Now, what do we notice? They're both going to be waiting, and both are waiting for one another. Stuck waiting. We could say, is this a deadlock? Okay, so the race condition leads to concepts of locks. And a lock is just acquiring a value and releasing it when you're done with the transaction. Is this an example of a race condition? Oh, no, it would be a deadlock. One sec. About a deadlock, yeah. So race conditions lead to concepts of locks. Which lead to concepts of deadlocks. Now, how to resolve deadlocks? Detection of deadlocks with graphs. So you can generate acquisition graphs. So A acquires X, and yeah, so if you have a graph, let me put this on draw. So if you generate a graph as you're forming transactions, you can look for cycles. So is this just a drawing thing? Calligraphy, okay, so it's white. Okay. So we have A. We have A. It's pointing to. And you'll see why this is the simplest example. A is pointing at X. Oh, is that how they get the X logo? It's just calligraphy? Wow. Is Elon Musk an artist? Probably not. He probably hired somebody. That person just used calligraphy one time. B is pointing to Y. And you don't know if the system's in a deadlock because maybe like transaction B is doing some more steps. Like, actually you would know because both the transactions won't be doing any more steps. But this is basically the idea of a deadlock. Is there a cycle? So A tries to acquire Y, B tries to acquire X, and let's pick a different color now. We have a cycle, which is A goes to X, goes to B, goes to Y, goes to A to X. That's a cycle. And a cycle is a deadlock. Cycle. Okay, whatever. So you can generate these graphs to detect deadlocks. How else do you resolve deadlocks? We'll just ChatGPT it. Actually, let me guess and then ChatGPT. I guess that's a good way. So if a transaction is in a stalled state for too long, cancel it. And then one of these will cancel, and then one of the other transactions will complete. But yeah, let's just see. Blah blah blah. Deadlock prevention. Yeah, so this is actually pretty annoying. So the first option is eliminating circular wait. This takes a lot of processing. And which is force a strict ordering of resource acquisition. Because like say A needed the value of X before it needed the value of Y for some other thing. So I don't know how easy that is to implement. Oh yeah, this is a good one. Avoid hold and wait. Declare all resources a transaction requires. If any are in a lock, don't. And then you can detect locks. If any are acquired, and said transactions that have them acquired. So this can get confusing because then you have we have multiple transactions. So A acquires a bunch of stuff, and then one of those values are in B, but there's no values in B that are in A, but there's some values in B that are in C, and those values are in A. So we can get really complex deadlocks. What are they saying? Okay, so acquired, don't run yet. So we stall the transaction completely until the resources are available, because it's not just simple as A and B, because you might think check if any of the resources A needs are in B, and if any of the ones B needs are in A, and you will resolve deadlocks. But deadlocks can happen with like as many transactions as you want. You can have a deadlock loop of like 100 transactions trying to do something together. It's unlikely, but it's probably going to be like something like 4 or 5. Actually, it depends completely on the system you're building. So that's why they do avoid hold and wait. It just checks, is anything A needs in any of the transactions that are currently running, B or C? Are any of their resources already acquired? If so, then just don't run A until B and C are done. Or whatever, if B has some resources A requires and C has some resources A requires. So any transaction that has resources A requires, finish them before running A. Okay, what else did it say? Okay, yeah, so read only resources. If you're reading a value, if you're both just reading a value, there's no issue. So deadlocks are actually any race conditions are caused by read-write mismatch. So if you're both reading from it, there's no mismatch. If you're reading but one of them's writing to it, there's a mismatch. If you're both writing to it, there's also a mismatch. So there's a good graph for this. Read, write, race condition. Table. Dude, who cares? Okay, basically, something I remember from distributed systems. Let's see what else there is. Preemption. Transaction hate rules tries to be the system can preempt the resource from transaction A. Oh, okay, it's just killing one of the locks. So killing one of the transactions. Detection, discovery, wait for graph. So this is what I was talking about here. This is kind of like for detecting deadlocks. Something like that. But it's a little bit different. You're talking about what you're waiting for. It's the same thing, honestly. It's the same thing. All of these concepts are not complex. So we have A is waiting for Y. A is waiting for Y. B is waiting for X. They call it a wait for graph because you think about what wait for and then you think about what acquires what. So you can form the directions. So you can say X is acquired by A, B is acquired by Y, and the loop, well, we can do that in red. The loop is X goes to A, goes to Y. Actually, no, I drew the second arrow wrong. Let's see, so B is acquired by Y. And then if you look at the graph lines, you can see how the information kind of flows. X is acquired by A is waiting for Y is acquired by B is waiting for X, and we have a loop. So let me make that a little bit outside of the system. That is a loop. Let's take a screenshot of that. We can add it to this. And this is just from the example above. Yeah, but using ChatGPT for learning is good. Just don't ask for all the answers. You know, think of it a little with this. It's like all the ideas are already predefined for you. But really understand how it works. If a cycle is detected indicates a deadlock, process termination. So resource preemption, release the specific resource, let transaction B complete, and then add transaction A back in, roll back to a safe state. Banker's algorithm. That's actually pretty cool. I don't know this, but we can put that on a to-do to learn. It's just an algorithm to detect any issues with resource allocation. Yeah, this is basically another thing. Timeout. Yeah, so you just have random timeouts to retry transactions. Because if you have the same timeout, say both of them get stuck, they both retry at the same time, and they get into a deadlock state again. So usually you have random amounts or some random value to say how long should we wait until we retry. Okay. Acid. So this is basically what acid is. Or atomic is. My bad. All or nothing. So complete all the transaction or none of it. So a transaction could be update my bank information. Like I did a transaction. Either it all, let's say, succeeds or all fails, because you don't want to do something like only part of a transaction, because then you'll get into a state that's invalid. For example, transfer $2,000 from account A to account B. The issue with this is A will, so what, break this down. What does this look like? It's like, read if A has enough funds. The issue is always with write. Write A minus 2,000. Oh no. Failure here. Now, suddenly, if you just stop here, transaction, we just have A lost 2,000, B gained nothing. So that's why they usually want atomic. That's a simple example. The database is always in a consistent state. So yeah, you could read that and be like, we gotta ask yourself, what does this mean? I don't know, man. Consistency? Consistent state. Yeah, actually, I don't know. Oh, consistency. You don't want mismatches. Okay, so this is a good segue to the next topic. Mismatches between multiple database instances. So there's never one database. It's always like your primary and then your secondary or your follower nodes. So some examples are the master-slave architecture. So you have your master DB, and then you have your nodes that try to follow it. So say if your master database suddenly fails, you still have your nodes that are reading it. So this could look something like, let's clear this all. Yeah, people thought this was racist when GitHub was like, oh, we're going to call it the master branch and the slave branch. I think some people got mad about that, but I don't even get the big deal with calling it master. Like, I mean, why call it master in the first place? Main just makes sense. This is your main branch. So I understand why they're mad, but I don't think it's something to get that mad about. But, you know, maybe it's just because I'm not part of that group. I don't get it. Which is fair, you know. I'm an outside observer. So how does it usually work? They call me Sonic. Yeah, if I end up not getting a job that I like, I think I might just try to do a neat code thing and make videos every day explaining concepts, because it's kind of fun, you know. I feel like Fireship, neat code, this is all pretty cool. So these are requests. Let's say read is red, so or write is red. So and let's say you're sending in a write request to the database. So you only want to write to your master database, and your nodes, this database will send write requests to the rest of the databases to read in the values and store them properly. So that's makes sense, but then the situation occurs, and let's make the situation orange. If this one, and that's another note, you can read from any of them, because ideally they'll all have the recorded value. So you can read from any of them. But say if this one goes down, you just elect a new master to say, hey, now this one's master, we're going to write to this and we're going to read from it. But this is like a very simple master-slave architecture. What usually goes on is like a more complex one with multiple databases. But I think the next big thing would be children's books to explain concepts like distributed systems. And you like make a children's book explaining it in a kid-friendly way, and now your kids know like leader election, read, write, quorum. That'd be a cool project to make, honestly. I think I'd give that to my kids if I had kids. Okay, now we're gonna do something called quorums. So what are quorums? So there's read quorums and write quorums. So this goes to a concept of quorums. Read/write quorums. So read quorums. Dude, being a teacher would be fun, bro. That'd be chill, bro. So, but I don't think it's that fulfilling, you know. It doesn't pay that well. I mean, it's fulfilling, but not a lot of impact. So you just set these as like values. Ideally for read, you just want n over 2. Actually, you play with these values. So say you have n is equal to your number of databases, right? So read, you could say you make a trade-off between available and consistency. So this is availability, consistency, trade-off. And this is already very partition tolerant by design, because you have multiple databases. You have like n storing the same value. So if you write to n over 2 databases, so if your write value is equal to n over 2, that means you need a successful write on n over 2 databases to commit that write. So you got the idea of committing it. So you can try to write, but if less than half of the databases accept that write, then you just cancel that transaction. So this is again on with transactions. Or you can say read is just n over 2 as well. You need to read successfully on n over 2 databases to commit that read. And then you can play around. So if write is equal to 0, you have highly inconsistent but fast writes. If read is equal to 0, again, highly inconsistent but fast reads. And if you have something like read quorum value is greater than the write quorum value, then you'll likely have lots of failed reads. So I think ideally you want write quorum to be greater than read quorum. Why do we want this? So the idea is if your write quorum is equal to 2 and your read is equal to like 6, that means you only have to write successfully to 2, but you have to read successfully from 6. That's ridiculous. If you only need to write successfully to 2, but read successfully, you have like min number that need to be correct is 2. Now if you read, that'll mean a lot of misses. Misses as you need 6 correct in read. So you see how write affects read? So we want write is less than n over 2. Yeah, ideally. And then if you want, those are just some arbitrary values you could set. You could set it higher than n over 2. Why do you want more than half the databases? That's for consistency. So why have write greater than n over 2? Let's bold this, consistency. always pick where more than, so less than or equal to. Always want more nodes to have correct values than incorrect. So an example is like have read and write both greater than or equal to n over 2. Because in the worst case, greater than or equal to, because in the worst case, you write to n over 2. And in this case, you read from n over 2. So what read and write quorum are actually just a value, and you want it to be greater than this value. So greater than is kind of confusing. Read quorum at least n nodes, half read quorum of n, have to have this value to read successfully. And then write is similar. Okay, so that's basically how quorums work. And every time you send a request in, this one sends this request to all of its friendly nodes that it knows, and you're like, oh, how does it pick to send to this node? Either you can do some leader election, but it's simpler to say that whatever node that gets sent the value is the leader, and we're going to base it off whichever database is closest to you will be the one that you hit. So it'll hit all these will return, hey, did I succeed, did I fail, did I succeed, did I fail? So it will like return this, hey, I succeeded, I succeeded, I succeeded, I succeeded. Hey, okay, great, we meet our read quorum value, we can start, or read or write, doesn't matter. We can either read or we can return, yep, it successfully worked. Okay, but that's that. Should I just throw this in here? Okay, great. Okay, now we're on consistency. What is the third one? Third one was isolation. Isolation controls when and how changes by made. Dude, bro, the ChatGPT descriptions are kind of terrible. Isolation, one transaction can't affect the other. I think that's what it means. So no race conditions. That relates to deadlocks. Let's ask ChatGPT. Explain isolation. Yeah. So, yeah, it's no race conditions. This one is winner, genyo, winner, genyo. So, yeah, avoid race conditions. And how do you avoid race conditions? You use locks. How do you avoid, what issues come with locks? Deadlocks. And we talked a bunch about deadlocks. So we can move isolation here as well. Read section on atomic. Last one. So A and I are kind of similar because they talk about the same things. Durability. This one's actually the easiest. This one's so dumb easy. And the idea is have backups of your data, silly. So that's my description. Let's see what they say. You sure all transaction results are permanent? Yeah, so just have backups of your data. This goes back to quorums. Master slave architecture, or like multi-node quorum architecture. Everything can be explained by multi-node quorum architecture. So even master slave. So in master dash slave, for what is your write quorum value? So that's a good practice. Just looking at different ones to see what is your write quorum value and your read quorum value. Number of nodes. Read quorum value is just 1, which is the database you look at. So if you write to all the nodes, then you could read from any of them. Because if your minimum condition is array has to propagate correctly through all nodes, then all nodes are consistent. So you lose out on speed of transactions for consistency. So availability loss to consistency. And again, there's you don't have to have this as your master slave architecture. This is just an example with high consistency. And you can read from any of the other ones. And yeah, if you think about it, it's the same. And people say, oh, you write to your master and the reads propagate. But that propagation thing doesn't really matter. As I explained here, this also kind of looks like a master slave architecture, right? These are the slaves. But in this case, it kind of like builds upon it by saying anyone can become the master, and it basically matters where your request comes in. So if you're in Europe and your request goes to your Europe database, why the hell would you go to America for your request? It's way further. So go to Europe. This is the master. Everyone else is now the slave that has to copy your commands. Yeah, so you can see how it's all really the same. Okay, so we're done ACID. Let's go over to the system design interview. So let's just skip through it because I'm not gonna waste too much time listening, because videos are honestly not the best. They're too slow, and then when you speed it up, it's like hard to hear. But reading is always the best. So read a textbook next time you need to study for systems design, and you can learn distributed systems. But these are questions they ask, so you gotta watch them. Transmission. Dude, this is like built on top of like TCP. Like they'll never ask you TCP stuff. TLS security. Oh, it's built on top of UDP or TCP? Or TCP. Transmission control protocol, yeah. It's built on TCP. Okay, yeah. So if you go into networks, you can talk about like lost packets, your sliding window of how many which packets you're sending, ordered data delivery. See, there's so many topics you can learn about. UDP has its own security layers. I think HTTP 3 or HTTP 2 is built on UDP. But they build upon it to it's built on TCP. Never mind. Quick UDP internet connections. Prove upon. Oh, okay. Yeah, so HTTP 3 is considering using UDP over TCP, and TCP is like, I want to network. Computer A wants to access computer B, so it knows about computer B, sends a message out. Computer B gets it, and then it sends a message back, and then you can start sending messages. Actually, how does it work? UDP just sends out a message request, and then the node that's trying to replies. So it's a lot faster. Let's see. Going for TCP. Yeah, reliability, consistent control, lower latency. Okay. Explain three-way handshake. Actually. So UDP kind of like broadcasts the message. We can see here, how does TCP work? Okay, yeah, so TCP has this first connection message. Hey, sender wants to send to receiver. Receiver responds, okay, sender, let's start sending. And they send. UDP just kind of broadcasts it and sends it back and forth. Okay, unreliable delivery, response, yeah. Okay, acknowledgement, yeah, reliability, no congestion control, no order delivery. I see, so there's no acknowledgements being sent in UDP. So in TCP, it kind of checks if the system's up, and if the system's up, it returns an acknowledgement. With UDP, it doesn't do that. Okay, I gotta go over networks, but I'm not applying any network jobs. I'll read over my networks textbook. I'm trying to finish some of these interviews that are kind of a pain. Okay, so we don't have to worry about that. Alright, what we do gotta worry about is system design interview.
Next is a server-side encryption, because you want to store messages securely on backend host. Messages are encrypted as soon as front-end service receives them. Messages are stored in encrypted form, and front-end decrypts them only when they are sent back to a consumer. It means that like when once front-end service has many responsibilities, or not, front-end host calls a randomly chosen metadata service host, because all the cache nodes contain the same information.
Okay, so then this is another layer of abstraction, which is there's not going to be one metadata service. We're going to have multiple, and we're going to partition by some value. So we shard our values based on, I don't know, maybe their front end service that they hit. So A to Z, this is mapping. Maybe it could be anything. It could be their ID, and you're mapping, oh, their ID starts with A. It starts with a character, so go to this metadata service, but you gotta have some good way of determining how to hash between these, because if all of them are hitting one service, that's pretty bad. Usually they, I know Kafka does it automatically for you because all the IDs are pretty unique. So that messaging queue, it like splits between whatever services it requires pretty effectively. Blah, blah, blah. This one is like just partitioning based off letter. That's an example of that. Oh, yeah, that's not usually the best, but it doesn't really matter. The backend service. So this is in cluster manager. Okay, so this is kind of what I was telling you before about how there's a backend, but it's not made by a single database or a single queue. It's made up of leader followers. So there's a higher level of consistency and not consistency. There's actually ends up a lower level of consistency unless you require like it partitions perfectly. So this is a great example of the CAP theorem. Let's start initially. If you have we're going to explain the CAP theorem in 3 minutes. You have 5 nodes here. Now imagine you just have one for your backend service. That is high consistency and high availability, but it's not partition tolerant. If there's a network failure and B fails, then you're in a bad state because now your front-end service has nothing to connect to. So that is consistency and availability, but not partition tolerance. Now let's talk about availability and partition tolerance below consistency. This would occur if you have a set of nodes replicating values, But if you have lower consistency, that means you have a lower write quorum value, so a lower requirement to write and read values. So write quorum and read quorum would be low. So lastly, if you have consistency and partition tolerance but low availability, it means your write quorum and read quorum are quite high, so it takes longer for transactions to go through. And some transactions might not be available all the time. Like if you want to read, or if you want to write, and your write quorum requirements are quite high, it lowers the availability because it's going to try and retry. It's not going to be as fast. So we get a good breakdown of the cap theorem right there. And you think, what's the best way? Usually it's a trade-off between consistency and availability. Like you lower your requirement for consistency to make the whole program more available. Somewhere between those, consistency and availability. And you also reduce consistency by making the system more partition tolerant. So that adding more nodes makes it more partition tolerant. So you lose out on resources and consistency, because with one database it's always going to be consistent. But with quorums, it's always like consistency and availability. And the more databases you have, the more partition tolerant it is. So yeah, that's basically it.
When sent the service to identify before
so option A is a leader follower. That's what I explained, and now this is independent host. So you can have any of them, and they have an in-cluster manager and an out-cluster manager. So you have B is the leader, and A and C are the followers. D is the leader, and B and E are the followers. So it just selects some nodes to replicate itself on. Over here, out cluster manager. Oh, so this one, it's multiple clusters, so individual clusters. I actually like option of individual clusters better, because this one is harder to debug. Because if you want to see, where's the issue occur with hitting this backend service? We have to see which leader host was you looking at, and then which leader host was you looking at. Let's see what its replicated nodes were. Its follower nodes were. But in here, it's a lot simpler, because it's just like, hey, this is one independent cluster. This front end service is hitting this independent clusters. There's nothing outside that we need to ignore. But with this one, we gotta see what it's hitting and then see what to ignore as well. So let's see. Yeah, there's no leader and follower issues with the out cluster manager. Also, that's pretty good. First in, first out. If you know networking, you can learn about how packets are ordered, packet ordering, and then you can figure out how to do first in, first out for messaging queues. This is the same thing. So each message is a packet, and we want the ordering of the packets to be correct. And even if one packet arrives first, we want the ordering to be fixed. Like I remember on LinkedIn, I received 2 messages from somebody, but the second message appeared first, and then the first message appeared and shifted the second message down. So you could see they're doing some message management there, where they want to show you the most recent messages, and then the rest of the messages load in. So if you don't know how to do that, look into how packets are transmitted in networks. Okay, let's see this outro.
To the interviewer. Many times this topic is omitted by candidates, but it's very important. Let's take one final look at the architecture we built and evaluate whether non-functional requirements are fulfilled. Is our system scalable? Yes, as every component is scalable. When load increases, we just add more load balancers, more front-end hosts, more metadata service cache shards, more backend clusters and hosts. Is our system highly available? Yes, as there is no single point of failure. Each component is deployed across several data centers. Individual hosts may die, network partitions may happen, but with this redundancy in place, our system will continue centers. Its messages are not lost during the transfer. Thank you for watching this video. If you have any questions, please leave them in the comments below, and I'll see you next time.
Dude, what a goat though. Notification service. Yo, honestly, I don't know what I'm studying. This systems design, it was just one question that messed me up. which was a tiny URL shortener, and it was because I got in my own head.
And welcome to the system.
But realistically, it's pretty simple. Like I got my own head about DNS and how that works, but it was just redirects. Let's see, notification service. So we have pub sub. You could do polling for updates. You could do WebSockets. If it's pub sub, you probably want just polling. So functional is you want to be able to create a topic, publish to it, and subscribe to it. Publish, subscribe. So this could even be a Reddit thread. You create a Reddit thread, you want to publish it. Non-functional is always the same. Everyone wants the same thing. They want it to be scalable, performant. It's kind of like business value. Scalable, you want a lot of people using it. Performant, you want people to enjoy using it. Durable, you want to resist system failures. Consistency is usually not as important unless you're working with sensitive data. Like if you're a bank, then you really want consistency over the other ones. It's just what you value the most. So availability, you never want your systems to be down. Everyone wants availability. But some banks will actually prefer consistency over availability because their utmost prerogative is to be extremely consistent. You should never show incorrect information in a banking app. Scalable, performant, consistent, and durable. No. But yeah, not consistent because it's not a big deal if you have incorrect information or outdated information. Okay, so he starts all of these videos with the same idea that, hey, you're some user. Now he doesn't go through a virtual IP. I think the virtual IP thing is kind of like, it's a bit too involved. It's like, how do you send your data to a load balancer because there's going to be multiple load balancers? Like you could say that, or you could just say, hey, you know, instead of, we send it through some other way. So we can send it through IP addresses as well. So everything in this IP address will be sent to this database, but virtual IP addresses are fine too. Probably a good reason to use them. But yeah, so there's always the same authentication type of system. So send it to your load balancer. We need to authenticate, hey, is this a valid request with our front end service? So we need some user stats about topics and whatnot. So before we check the database, we use a metadata service because we don't want to touch the database directly. And that will touch the database of like topic information, who's published to what, who's subscribed to what. Let's skip through. Okay, yeah, again, request goes through a reverse proxy, find just, yeah, this is too involved, honestly. So this reverse proxy will go to a front end service, local disk and cache. It'll store service logs, metrics logs, audit logs. So it'll just store metrics. So this front end service basically just stores metrics about topic, subscribers, messages, basically about you. Say like, hey, he subscribed to this. A caching layer and okay. So this is what Zookeeper does. Zookeeper is a configuration service that handles what is it? Actually, let's see what Zookeeper does. Let me see. But my guess is Zookeeper is a configuration service that handles multiple nodes, quorum reads, quorum writes, stuff like that. leader election, atomic operation. So atomic operation. Let me dumb this down. Leader election is picking. Picking who you're writing to and who's like coordinating, sharing that information. So these are basically, this is master, setting master, setting slaves, have some pub sub model where you can subscribe to the master and see what happens. Atomicity, consistency. Fault tolerant, quorum. So yeah, that's the main thing. Oh, and Zookeeper has a single point of failure, which is the leader. That's not good. But let's hear what he has to say about it.
Combination of a topic name and topic owner identifier. Based on the hash value, front-end host picks the corresponding metadata service host. Let's discuss in more details two different approaches how front-end hosts know which metadata service host to call. In the first option, we introduce a component responsible for coordination. This component knows about all the metadata service hosts, as those hosts constantly send heartbeats to it. Each front-end host asks coordination service what metadata service host contains data for specified hash value. Every time we scale out and add more metadata service hosts, coordination service becomes aware of this change and remaps hash key ranges. In the second option, we don't use any coordinator. Instead, we make sure that every front-end host can obtain information about all metadata service hosts, and every front-end host is notified when more metadata service hosts are added, or if any metadata host died due to hardware failure. There are different mechanisms that can help front-end hosts discover metadata service hosts. We will not dive into this topic here.
Okay, I see what it means now. So you have all of these services. What happens if one of them dies or one of them comes back up, or if there's a new one? So it's either the front-end host interacts with all of these services, and each service interacts with the front-end service to like tell them, hey, I'm back up, I'm down. But I guess it's better to have a coordination service that can coordinate for you, kind of abstracts that logic out, so you don't have to handle it on your side. And it's like a central registry of what are the living nodes, and what are the conditions for quorum for a write to occur. So it goes to the service and tells the front service like how many nodes are available.
Here, when you mention the GOSA protocol, this protocol maps data service host. Coordination, each front coordination. This constantly send heartbeats to it. Each front-end host asks coordination service what metadata service host contains data for specified hash value. Every time we scale out and add more metadata service hosts, coordination service becomes aware of this change and remaps hash key ranges. In the second option, we front-end host data host died due to hardware or metadata service host. This protocol is based on the way that epidemics spread. Computer systems typically implement this type of protocol with a form of random peer selection. With a given frequency, each machine picks another machine at random and shares data. After being initially processed by the front-end service, messages then passed to the temporary storage service. Why?
Still kind of confused actually. I mean, I get it. Alexa leader, which is you go to the configuration service to see what database you should hit. The database is why can't the services just return whether a write/read is correct? Okay, I got it. So basic idea is each service does not know how many services they are. So your quorum read and quorum write values are kind of unknown. So say if 3 services go down, then all of your writes and your reads will fail. So you need some configuration service to say, hey, you only need 3 writes or you need 3 reads. So you didn't draw the arrows, but these are probably pinging the configuration service for more information about what is the number of nodes that we have available, what's the hat, and what is the requirements for a read to occur and a write to occur. And these are all sending heartbeats to configuration services to tell them what's alive.
Epidemic spread. Computer systems typically implement this type of protocol with a form of random peer selection. After being initially processed.
Yeah, what if somebody asks you what's your gossip protocol? I think it's just like select a random peer, share information. But how long do you keep on doing that? I guess if your node that's already received the information, don't propagate it forward. It's kind of like depth first search. Oh, actually, maybe they just pass around the value of how many nodes have the information. And once all the nodes have the information, then it's good. Let's see, acid protocol. Bro, I wish there was like a step-by-step explanation. Actually, let me just chat GTV. What is the condition for stopping a gossip protocol? How do you know all nodes have information? That's what I'm really confused about. What stops it? Yeah, so if the node's already received the information, don't gossip. Oh yeah, so this one is just stop after a fixed number of rounds. The fundamental constant, eventual consistency. All nodes will eventually converge to the same state. Timelines and heuristics, quorum and consensus. Let's see what eventual consistency looks like. Yo, bite by go, man.
Today we will be talking about the eventual consistency. We've talked about the consistency in 2 different videos on this channel. The first was when we talked about the ACID compliance. In ACID, the consistency means that when inserting the new data. Consistency when we, and the eventual consistency in terms of a distributed or more systems. Service, there might be a separate for now. Let's say the number of orders that they have placed and so on. So what would be the consistency in this system? Consistency in this system would mean that whenever we place a new order, the stats API should have the valid count for the number of orders that the user has placed. For example, if I have placed 5 orders, the stats API should return and tell me that I have 5 orders. On a high level, there are 2 different ways of achieving this consistency. First one would be to update the order count, telling them that the order has been placed. In this way, whenever we'll have a new order, we will keep updating the order count in the stats service. And one issue with this approach. Let's say that our stats service has a lot of complex logic and it is busy making sure that whenever I'm going to be inconsistent because we're checking for the new orders and keep updating the order count in the stats service to make sure that for some time, but it is eventually going to consistency is having the system in an inconsistent state.
Okay, that makes sense, but I kind of want it in relation to a gossip protocol. Fine.
Okay, so let's visualize it. It's pretty simple for the most part. All we're going to do is pick a few nodes randomly, broadcast any message that the original node has to them. Keep in mind, and broadcast it to them. Expected in the next round, membership and failure in a cluster. Node is still going to reach one of the new nodes. So now we've got 3 new nodes infected in the next round, which are going to go ahead and randomly keep trying to tell other nodes, and eventually, boom, okay. Everyone knows about the message, which is great. As you can see in large clusters, after a few rounds of running this gossip protocol, we can generally get our messages all around. So why is this useful in Cassandra? Well, basically...
Okay, see, all these guys talk about it, but do you know how I know they don't really know about it? But they're just like, they're just talkers. They don't talk about the stopping condition.
Which are going to go ahead and randomly keep trying to tell other nodes, and eventually, boom, okay. Everyone knows about the message, which is great.
Everyone knows about the message, but how do you know everyone knows about the message? I guess you only... I guess they should explain this, but what I think is you don't... If you send it to... If you're a node that already has a message, you don't send it out. Now, the second question I would have is what happens if you kind of get into a loop where these ones randomly select two nodes, but those two nodes have already seen the message, so the broadcast doesn't continue. So if you have that first condition that you don't send if you've already got the update, and the second condition, I guess you have to check over all your neighbors, filter out the ones that have the update, and send it to the rest of them. Or just rely on the fact that it's probably going to work because you're randomly selecting them. So say this last node, nobody randomly selects this last node right here. Then it's not eventually consistent because that last node doesn't have the value. I swear I learned about this in networks, but people don't.
So if like how many writes I'm taking in, and if I'm kind of like looking like I'm gonna crash, each node is also receiving heartbeats from other nodes incrementally via this gossip protocol, and it's going and saying, okay, I've received a heartbeat, here's the timestamp of the heartbeat that I received, and keep in mind though that obviously the issue with these timestamps is that server timestamps are not always coordinated, so that can be problematic there in terms of ordering messages, but that's just something to keep in mind. And then other nodes upon receiving gossip will use those timestamps to basically say, okay, I see that node 1 received a heartbeat at 12 o'clock, but node 2 received a heartbeat from this other node at 1 o'clock, so I'll keep the 1 o'clock timestamp, and that's the most recent anyone's ever heard from that node. And so it's going to hold on to that timestamp and basically use those timestamps for each node locally to try and guess if that node is still up or not. So if all of the nodes are assuming that a node is down because no one's received a heartbeat from it in say an hour, then eventually they'll stop sending writes to it. So yeah, that's basically how gossip protocol gets used in Cassandra, but generally speaking, gossip protocol is just a good low overhead system for communicating messages to a bunch of nodes in a cluster, and it's got
yeah, I remember learning about vector clock, but I completely forgot that. Hopefully this next interviews that I have won't ask me that. Hopefully that star was good to ask me. That's the one I want to actually work at. But honestly, at this point, you just got to find somewhere cool to work, wherever it is. Just keep on watching the video.
By the front-end service, message is a data persistent, so that messages survive unavailability of a subscriber and can be delivered later. Several design options can be considered, and this is a great opportunity for you to show breadth and depth of your knowledge to the interviewer. Let's see how many different directions the interview may go from here. You can start discussing databases with the interviewer. Consider pros and cons of SQL versus NoSQL databases. Evaluate different NoSQL database types, and give specific names to the interviewer. For example, when we consider SQL or NoSQL for storing messages, we may mention that we don't need AC transactions. We don't need to run complex dynamic queries. We do not plan to use the storage for analytics to run complex dynamic. We may mention that we don't need AC transactions. We don't need to run complex dynamic.
Why don't you need ACID? Because they're transactions. Because they're notifications. Actually, why don't you need ACID?
We may mention that we don't need AC transactions. Specific names to the interviewer. For example, when we consider of SQL versus NoSQL databases, evaluate different NoSQL database types, and give specific names to the interviewer. For example, when we consider SQL or NoSQL for storing messages, we may mention that we don't need AC transactions. We don't need to run complex dynamic queries. We do not plan to use the storage for analytics or data warehousing. Instead, we need a database that can be easily scaled for both writes and reads. It should be highly available and tolerate network partitions. Summing all this up, it is clear that NoSQL wins for our use case.
Why does NoSQL win? We're not doing any complex transactions with the data, so NoSQL is good at joining tables. Oh no, SQL is good at joining tables and saying you want this data from this information, this data from this information. I guess notifications, it's you're never doing operations on multiple notifications. They're kind of standalone for each thread.
If we need to choose a particular NoSQL database type, we need to mention that messages have limited size.
There's no reason to use SQL in this instance.
Let's say not more than 1 megabyte, meaning that we don't actually need a document store. And there is no any specific relationship between messages, and thus we can exclude graph types as well, which leaves us with either column or key value database types. And we can mention several well-regarded names of these two database types. For example,
key value, this thread has this notification.
Apache Cassandra and Amazon DynamoDB.
Oh yeah, see, I'm not gonna know that.
Next option we can evaluate is in-memory storage. We better choose an in-memory store that supports persistence, so that messages can live for several days before being dropped. And also mention some great in-memory storage solutions, like Redis. One more option to consider, message queues. Distributed message queues have all the characteristics we require and also can be discussed in more details. To be prepared for this conversation, if you want to further impress interviewer, you can talk about other options. For example, stream processing platforms.
If you ever need to know if you should use SQL or NoSQL, think about how many operations you're using on different tables. So if we made a SQL, we'd have different tables of different notifications. Are you doing any transactions, any computations on them? Anything with joining tables? No, then just use NoSQL because it's simpler. We're just passing information through. Column graphs. I guess, again, we're not querying stuff from our database, so there's no reason to have that added complexity. So is GraphQL a NoSQL database? I think it is, actually. Oh, wow. Wait, is GraphQL a NoSQL? Oh, it's just a query language. Oh. Oh, I always thought GraphQL was like a... Is GraphQL SQL or NoSQL? Okay, so I guess it's just a conversion layer, whatever. Oh, it's just a query language. I see. So it's agnostic. I didn't even know this. So I thought GraphQL was like worked only on NoSQL, but really what it does is you put in your command, what I want. It goes into GraphQL and then converts it to SQL command for SQL databases. Because you're not gonna set the commands yourself. You send it to GraphQL, or it can give you your NoSQL command to fetch data. Oh, I didn't know that. It's a query language, not a data format, not a database type. Oh, that's pretty cool. Okay. Yeah, I should have seen. Give me an example of GraphQL converting a request to a series of SQL commands that it uses. Oh. Okay. Data fascination. Okay. Okay, so I get it now. So you don't want to send a lot of information to the user client side. So it's kind of like there's a client, there's GraphQL server, and then there's the backend. So what is it? Overfetching, getting a ton of data from backend you don't need, GraphQL will filter it. Need new endpoint to do something. Need new endpoint that's like a combo of others. GraphQL can abstract / merge commands for you. So this is kind of a trade-off, I'm guessing. So trade-off is GraphQL server cost still making the same queries, right? But the gain is that you don't need to develop a new endpoint. You can just adjust a GraphQL query. Let's check if that's right with ChatGPT. Okay, I understand GraphQL now. So that last time I used it was a long time ago. Long time ago. But I understand what GraphQL is. It's demystified. It's just a middle layer. That's all it is. For interacting with your backend. That's all it is. So if I had to make a project and I wanted a lot of computations, some of my personal projects have that, I'd use SQL and I use GraphQL because I don't want to make new endpoints all the time. And the server costs for GraphQL are probably not that high. Yeah, honestly, a good move fast type of technology.
Discuss pros and cons and compare this option with the distributed queue solution. And of course, don't forget to mention some best-in-class solutions, for example, Apache Kafka and Amazon Kinesis. Here we reference AWS solutions, but feel free to mention similar solutions from other public clouds, whatever solution you feel comfortable with. Out of these four options, which one do you consider the best? But I'm really curious what you think. On the sending DLC that we apply to subscribers. Let's take a look at the sender component. You will see that ideas on which the sender service is built upon can easily be applied to other distributed systems, and not just authentication service. If you design solutions that involve data retrieval, processing, and sending results in a fan-out manner, meaning that messages are sent by having a pool of threads, where each thread tries to read data from the temporary storage. You can implement a naive approach and always start a predefined number of message retrieval threads. The problem with this approach is that some threads may be idle, as there may not be enough messages to retrieve. Or another extreme, when all threads may quickly become occupied, and the only way to scale message retrieval would be adding more sender hosts. A better approach is to keep track of idle threads and adjust number of message retrieval threads dynamically. If you have too many idle threads, no new threads should be created. If all threads are busy, more threads in the pool can start reading messages. This not only helps to better scale the sender service, it also protects temporary storage service from being constantly bombarded by sender service. This is especially useful when temporary storage service experiences sending results in a fan-out manner, meaning that messages are sent to multiple destinations in parallel. Think of the ideas we will discuss next. The first thing that sender does is message retrieval. This is achieved by having a pool of threads, where each thread tries to read data from the temporary storage. We can implement a naive approach and always start a predefined number of message retrieval threads. The problem with this approach is that some threads may be idle, as there may not be enough messages to retrieve. Or another extreme, when all threads may quickly become occupied, and the only way to scale message retrieval would be adding more sender hosts. A better approach is to keep track of idle threads and adjust number of message retrieval threads dynamically. If we have too many idle threads, no new threads should be created. If all threads are busy, more threads in the pool can start reading messages. This not only helps to better scale the sender service, it also protects temporary storage service from being constantly bombarded by sender service. This is especially useful when temporary storage service experiences performance degradation, and sender service can lower the rate of message reads to help temporary storage service to recover faster. How can we implement this auto-scaling solution? Semaphores to the rescue. Conceptually, a semaphore maintains a set of permits. Before retrieving the next message, thread must acquire a permit from the semaphore. When the thread has finished reading the message, a permit is returned to the semaphore, allowing another thread from the pool to start reading messages. What we can do...
Okay, semaphores. So this is a concept a little like... Dude, I learned this concept too. It's crazy how some things will get stuck in your mind forever. But some things will just pass by. Like, I remember a lot of systems design, but semaphore is one concept I don't really remember. Yeah, I know it's related to deadlocks. So it's like an alternative deadlocks. This was like in our operating system course. We had to use semaphores for something. But let's just read a little bit about it. Explain semaphores. Integer variable, yeah. Yeah, okay, so I know a mutex semaphore. It basically just acts like a lock. Boolean just acts as a lock. So I should say deadlock. Alternative locks as a lock, and then we have an integer semaphore. And let's see. Serious scenario, we have 3 printers, 3. Oh, okay, I see. Consider scenario, 3 people. Okay, so this is more for count the amount of resources. So you have 1 available resource you have available. So say you have 10 threads, then decrement each time a thread is busy, increment each time a thread is free. You have a good thread is free. You have a good system of measuring when threads are busy / free. And if you guys want to get good at systems design, just use Excalidraw, because like all these interviews end up using Excalidraw. Oh, let's not look at my old sad systems. That wasn't even a system. That was me talking about, I don't even know what I was talking about. But use Excalidraw. After like I go through these videos, I'm basically just gonna tell myself, okay, now you're building this service. I'm gonna go on Excalidraw. I'm gonna draw it out, and I'm gonna compare it to the actual solution. This is how you get good at interviews. You literally just do interviews. So say, hey, this is my front end service, blah blah blah. That's how I got kind of good. But I'll draw on paper. Honestly, just draw on Excalidraw. Every interview is pretty remote.
No, it was just the number of this is dynamically.
We kind of got an idea, and then you can, based on if a semaphore is 0, you can scale down or scale up resources. Semaphore value, you can scale up or scale down. So if it's always like around 10, you're like, oh, scale down. If it's still not reaching like a lower value, you could be like, oh, scale down. Because we don't need that many threads to work. And if it's consistently near 0, then you need to scale up because you're very busy.
Based on the example, we already called it at message read rate. After message is retrieved, we need to call metadata service to obtain information about subscribers.
Okay, so message receiver, then we have metadata service, and that interacts with our, so databases are on the outside because this whole thing is a sender service. Metadata, unless there's like some cache or internal database that the server holds, that the service holds, but yeah. So this is for user information. Maybe I'll just remake these videos, honestly. They're great, but like, I feel like, yeah, they're actually great, but I feel like
Probably
if I
some of
explain it, you know, it's a lot more dumbed down because I'm not a staff engineer. I can explain it in a very simpler way. I can try to find a simpler way to explain it because I'm a simpler person.
You are wondering why we need to call metadata service here if we already called it in front-end service and could have passed information about subscribers along with the
So why do we need to call it here? It's because the temporary storage won't have access to the information, so we need to access it again.
message. Good point to discuss with the interviewer. One of the main reasons not to pass this information along with the message itself is that
Yeah, you don't want to store all that in temporary storage.
list of subscribers may be relatively big. For example, several thousands of HTTP endpoints or a long list of email addresses. we will need to store all this information with every incoming message, and our temporary storage service will need to pay this price.
So it's better to refetch than to pass all subscriber information. And you could talk to your interviewer like when this makes sense. So if it's like a one-to-one messaging, like peer-to-peer messaging, not peer-to-peer, but like you're messaging a person directly, that does not make sense because the metadata data would be quite small. But if it's like thousands of subscribers, then it makes sense to refetch it.
Should we just iterate all of them? After we obtain a list of subscribers, we can start sending messages to all of them. Can you think of a good way to do this?
Okay.
Should we just iterate over a list of subscribers and make a remote call to each one of them?
Yeah, that's what I would think, but that'd probably be slow. What you should do is you should broadcast the message.
What should we do if message delivery failed to one subscriber from the
Retry.
list? What if one subscriber is slow and delivery to other subscribers is impacted
Threads.
due to this? If you think about all these questions, or if interviewer makes you thinking about them, you will probably figure out that this option is far from optimal. The better option is to split message delivery into tasks, where each task is responsible for delivery to a single subscriber. This way, we can deliver all messages in parallel and isolate any bad subscriber. So, let's introduce two new components, Task Creator.
Oh, so you abstracted more and Task Executor.
And Executor. These components are responsible for creating and scheduling a single message delivery task. How can we implement these components? Create a pool of threads, where each thread is responsible for executing a task. In Java, for example, we can use a thread pool executor class. And similar to the message retriever component, we can also use semaphores to keep track of available threads in the pool.
Yeah, so use semaphores here.
If we have enough threads to process newly created tasks, we simply submit all tasks for processing. If we don't have enough threads available at the moment, we may postpone or stop message processing and return message back to the temporary storage. In this case, a different center service host may pick up this message, and that host may have enough threads to process the message. This approach allows to better handle slow center service host issues. Each task is responsible for message delivery to a single subscriber. Tasks may delegate actual delivery to another microservices. For example, a microservice responsible for sending emails or SMS messages. So far, we have discussed.
Oh, I see. So, and then you have multiple tasks. So this one is a HTTP one. This one is email. So you kind of split it up based on what type of task it is, because they're going to be handled different. So you have your own service for mobile push, your own service for SMS, your own for email.
Responsible for sending form they agree to with email owners or emails. All tend to be brought up during the interview. How to make sure notifications will not be sent to users as spam? We need to register subscribers. All subscribers need to confirm they agree to get notifications from our.
Oh yeah, spammers. We need a handshake confirmation. So that's you send an acknowledgement. Hey, you subscribe to this. They say yes. So you can't just add random people. Handshake, sub, pub. What other spammer things they do, even if they have a bunch of people into their subscriber list, we could rate limit them because they can't send too many notifications back to back. So rate limit on number of notifs per minute. Unless it's like one of those services where you're allowing a ton of Actually, yeah, you should have limit notifications. If you get more than 4 notifications a second, then you should rate limit them and slow down their processing.
Our service, HTTP subscription request, to avoid network issues.
Oh, duplicate messages. What does he say for that? I'm curious.
Confirmation message to the HTTP endpoint or email. Endpoint and email owners need to confirm the subscription request. When publishers send messages to our notification service, front-end service will make sure duplicate submissions are eliminated. This helps to avoid duplicates while accepting messages from publishers. But when the sender service delivers messages to subscribers, retries caused by network issues or subscribers' internal issues may cause duplicate messages.
So this is like that at least once. So we need to have some duplication layer to avoid like, hey, I received this
At the
message.
subscriber end. So subscribers also become responsible for avoiding duplicates. If retries cause duplicates, maybe we don't need to retry once message delivery. Our system maximum allowed delivered message monitored. It would be great if our
So here he talks about at least once, at most once, exactly once.
does first more time.
Message
To
order.
guarantee any specific message order. For example, first come,
You can have timestamps and then reorder.
first delivered. What do you think? Please stop this video and look at the architecture one more time. And the short answer
No, it does not do it because we're working with threads and some messages might be blocked. So if it's in temporary storage, unless you store it sequentially and then process it sequentially, it would work. But you know, when the task creator is busy, it might send it back to the service, and then something else might be processed that was occurred after that first task. So no, it doesn't. So you should use timestamps.
answer is no. It doesn't guarantee any specific order. Even if messages are published with some attribute that preserves the order, for example, sequence number or timestamp, delivery of messages doesn't honor this. Delivery tasks
But you can. It doesn't honor that, but you can update the messages. Like I was talking about that LinkedIn thing. With those timestamps, once it received those messages, it reordered it on the client side.
can be executed in any order. Slower sender host may fall behind. Message delivery attempt may fail.
Yeah.
And retry will arrive in the wrong order.
Good points. Good points. So message
Attempt
ordering
may
could fail because of why. It says failure.
fail.
Retry. What other issues are there?
Slower
Delivery attempt.
sender host may fall behind. Message delivery attempt
Sender host is behind. All reasons for failures.
may fail. Always publish, always deliver to the customer's ability. Do you design a scalable system? Yes. Every component is horizontally scalable. Sender service also has a great potential for
Oh, this is a notification service, so it just works one way. If it was a messaging service, that'd be a different problem. So this one is just we want to notify a bunch of people.
vertical scale. Contains relatively small and fast memory.
With messaging service, you use something like a distributed messaging queue. And it'll send messages back and forth.
We discussed several temporary storage design. Our center will be stored machines, and ideally across several data centers. We also retry messages for a period of time to make sure sessions. Please leave them in the
Oh yeah, so some concepts everyone should know is noisy neighbor. Someone is spamming your service. It depletes resources for others. So if someone's spamming your service and you don't have some order for prioritization, then that person will eat up your resources and a whole bunch of other people will have a poor experience. So how do you avoid this? You have prioritization of messages or requests. So maybe every time they send a request, their next request has less priority until some back off time. Yeah, I made that up, but it's good enough. It's good enough. It works. Limited resources. Oh wait, isolated. Let's say isolated resources per person. Rate limiting, of course. Like maybe like 500 requests per minute. GitHub is rate limiting because I used to use the GitHub API for some marketing tactics, and yeah, you gotta find ways to avoid the rate limits, but or just set up jobs to run in the background so that comply with the rate limits. Leaky bucket algorithm. So basically you have a bucket of tokens The tokens refresh every, like, one token. Let's just say like one token is added every 10 or like 15 seconds. You have like 10 tokens to start. You can, this is also just rate limiting. You can make like 10 requests, but you have to wait 15 seconds for a token if you don't have any. So one token is equal to one request. So let's see, leaky bucket. Smooths out traffic. You can use the theory. How it works. It has add to bucket. We take out network traffic. Oh wait, maybe I got it wrong. Yeah, I thought this was like yeah, maybe I'm misphrasing it with like token bucket. Oh yes, there's token bucket algorithm and leaky bucket. Jitter. Okay, so that was token bucket, and it basically like restricts like your request and their processing. So token bucket, you can make these requests, but at some point you're gonna run out of tokens, so then you gotta wait for them to refresh. Let's see actually. Okay, token bucket, telecommunications, 4 types of characteristics, reliability, applies packet reach or not, retransmission, delay, it denotes different applications, dollar delay in different degrees, jitter, bandwidth, scheduling, first in, first out, trap shaving, does not depend on target as a bucket full, then packets are discarded. Packets, so replace packets with requests, because this is a networks concept. So it depends on your tokens, does not depend on the tokens. Request is discarded, but not the packet. Token is discarded, but not the packet. Bucket is full. Okay, so I think I was thinking of leaky bucket, but I kept on using tokens instead of water. So leaky bucket. The host has to send packet and store in the bucket. Yeah, let's watch a video on this, honestly. Dude, bro, is there like some good videos?
Imagine you have a tap and a bucket with a hole.
This is basically basic idea is for networks, you want at some point you want a steady stream of output. So in my use case, we had a user trying to make a request to a database. You don't want to spam the database, so you only allow a certain amount of requests per second, and you store them requests that are pending. But if there's too many requests pending, just ignore those requests. We're not gonna handle them. Okay, so that's leaky bucket.
The force of the water from the application that is generating data. If it got burst size to it, packets will...
Yeah, and then if it overflows, those are the data. Those are the requests that you're not accepting. Let's look at token bucket algorithm, and let's look at images. Okay, token bucket. Yeah, this is a good image to compare the two. Rate limiting to add tokens in the bucket. Bucket which stores tokens. If tokens are available, outgoing data. Flow, we lose packets. Packets flow at constant rate. Oh, okay. So you're adding tokens. Oh, no. Okay, so I was talking about token bucket. We are consistently adding tokens, and every time you make a request, you say, can we make this request? If not, drop it. The thing with leaky bucket is we will store some requests that are still pending and ditch the other ones. But this one we will always ditch if we don't have anything available. I think that makes sense. Let's ask ChatGPT though to confirm. Does the leaky bucket have some caching level to store requests and try them, while token bucket rejects request and doesn't cache any? Question mark. Yes. Okay. They're queued. Okay. Okay, so I got it perfectly, guys. So you gotta really think about these things, man. Well, okay, so this is token bucket. So people will say, what's the difference between token bucket algorithm and leaky bucket algorithm? And people who don't understand it will regurgitate some geeks for geek stuff, and people will be like, okay, if you can't explain it in like to a 3-year-old, you can't explain it. So token bucket algorithm is equal to no caching. Ditch requests if you don't have tokens. Leaky bucket algorithm is caching. Only ditch when your request cache is full. But this is also like multiple things. Like this one is a, so this one has a unsteady, can have unsteady stream of requests. So you do 10 at once, then none. And with leaky bucket, you always have a steady, so you always have a steady stream of requests, which is why they added caching. Okay, so if somebody asks you what's the difference between token versus leaky bucket algorithm, this is what you tell them. Token bucket algorithm, there's no caching. You always ditch a request if you don't have tokens, but you can also handle an unsteady stream of requests. In leaky bucket, so you can allow, with there is caching, only ditch the request if your cache is full, but they always have a steady stream of requests going through. They have let's just say they have a max limit on the stream of requests going through. They don't always have a steady stream, because what if the bucket's empty, then you don't have any stream at all. But there's a max limit on how many requests can go per second. Now, this is better if you want to like avoid system overload. And this one's better if you want to avoid spammers. Now, this one's also good for spammers as well. But this one is like more for like noisy neighbor as well. Is it? Yeah, actually, this is just to avoid spammers. I mean, they both do it, but there's trade-offs between the two, is what I'm trying to say. So leaky bucket, you have the reassurance of knowing your like system load, but less freedom of so that's pros, reassurance, cons, less freedom of bursty behavior by users. So that's Let's just say so. Let's say leaky bucket has these pros. Yeah, so everything's pretty easy in CS. All you gotta do is understand it and then explain it to a 3-year-old. And then token opposite pros/cons of leaky. Okay, cool. Switch. Flip. Alright, so now we understand the two. We have our notification service video done. Rate limiting, bro. I don't want to do an entire video on rate limiting. I just talked about it.
Hi, and welcome to the System Design Interview channel. Today, we design a rate limiting solution, a popular interview request. Send the request to if we have a load balancer in front of our web service, and this load balancer spreads requests evenly across application servers, and each request takes the same amount of time to complete, requirements you need to do is to build a client identifier. With, or at least mention to the interviewer, each rule specifies a number of requests allowed is not exceeded. Interviewer may ask decision making. The thinking process has been pretty straightforward. We know we need a database to store the rules, and we pass to the rate limiter component that is
Okay, so the whole point of rate limiting is to avoid the noisy neighbor problem. So the first thing you need is something to client identifier, which will probably hit some database and get that information. So there's like probably like some client DB. Oh no, it's not. Would it be hitting a DB? Yeah, it should be hitting a database based on how many requests they've already done. And that information goes to the rate limiter, and the rate limiter uses the throttle rules cache and the throttle rules server. Why? Because the rules change as we go. So we cache the rules, and then as our services scale up or scale down, that retriever retrieves the new rules. Let's see. So token bucket algorithm.
number of.
Bro, we just talked about this. Okay, start job scheduler, makes a remote call to rule service, creates token bucket, and loads them into cache. Rules cache.
Per second to the bucket. All 4 allowed requests hit the cluster. We should throttle all the remaining requests for this second. But we still have tokens available. Tokens already, leaving host B with 0 tokens as well. And the same logic applies to host C. Now master balancers try to distribute requests evenly, but they don't know anything about keys, and requests for the same key will not be evenly distributed. Let's add load balancer into the picture and run a very simple simulation. The first request goes to host A, 1 token is consumed. The second request goes to host C, and 1 token is consumed there. 2 other requests within the same 1 second interval go to host B and take tokens from the bucket. All 4 allowed requests hit the cluster. We should throttle all the remaining requests for this second. But we still have tokens available. What should we do? We must allow hosts to talk to each other and share how many tokens they consumed altogether.
Okay, so this is an important note. When you have a distributed system and you have multiple services and you want to implement a token bucket algorithm or some other algorithm, how do we implement this algorithm to make sure that each host can make requests if it can and can't make requests if it cannot? So a token bucket, we give every node whatever n is, so n is equal to 4. We have the nodes communicate to get like an idea of the rest of the system. So it'll hit a service and be like, does it have nodes? But these nodes will communicate, these hosts will communicate with one another to update the amount of tokens each of them have.
A will see the tokens will be with 0 out, leaving it with 0 tokens available already. See. Now everything looks correct. 4 requests have been processed, each bucket 4 tokens. I bet you have a question. We hit our cluster. If many requests for the same bucket hit our cluster exactly at the same second, doesn't mean that 12 requests may be processed instead of just 4 allowed, or maybe a more realistic scenario, because communication between hosts takes time. Until all hosts agree on what the final number of tokens must be. May there be any requests that slip into the system at that time? Yes. Unfortunately, this is the case. We should expect that sometimes our system may be processing more requests than we expect, and we need to scale our cluster accordingly. By the way, the token bucket algorithm will still handle this use case well. You just need to slightly modify it to allow negative number of available tokens. When 12 requests hit the system, bucket will start sharing this information. After sharing, every bucket will have -8 tokens, and for the duration of the next 2 seconds, all requests will be throttled. So, on average, we processed 12 requests within 3 seconds. Although in reality, all 12 were processed within the first second. So, communication between hosts is the key. Let's see.
Yeah, so even if it gets to negative values, it just increases the amount of delay because you overturn, hey, we have negative tokens, and then you have to wait longer to make more requests.
How this communication can be implemented. By the way, ideas we will discuss next are applicable that is to most of them, which host use some configuration nodes every time this list changes. But the main
Gossip communication, distributed cache. Okay, that's how, okay, see, you should draw out these things. These are very, very important. This right here. And tell everyone everything is kind of, all of these are related to forms. So message broadcasting. This is actually the gem of this video. Right here. So one, actually, no, first message. So one is tell everyone everything. And as a practice, we can see, is this a multi-host quorum protocol? Or is this actually no, this is just message broadcasting. It's not related to quorums. So how do you distribute your message? Like this has been, this is my information. It's not about like deciding whether to commit that information or not. It's deciding how to distribute that. And then the next step is quorums. But first, how to distribute that information. But in this one, there is no quorums because like once you take a token and that request is being processed, you just gotta tell everybody. It's not like you can coordinate. That's why there's the issue of a lot of requests can happen at the same time. So you're not you're giving up some consistency for availability because you're allowing people to make more requests than is allowed, but the availability portion is you can always make a request if you have more availability. You can't always make a request, you just have more availability for the lacking that sometimes you'll make more requests than is allowed. So tell everyone everything. If all this, what does this require? This requires, you gotta think about like the complexity of these. So this requires that all nodes know about each other. So what does this require? All nodes know about each other. So that, what does that mean? They need to each store information and about each node, and they have to poll for heartbeats. Heartbeats. So if you don't hear a heartbeat from a node in like, I don't know, whatever period of time you decide, you can say that node's probably dead. Gossip protocol, we've talked about this before. How does it work? It selects a random list of neighbors it has to send the message to, and then that sends the message to a random list of neighbors it has until it's finished passing, but it only sends to neighbors that haven't got the message yet. So how does it decide like this neighbor hasn't got the message? If you send a message to a node that has got the message, it just stops sending. I think that's how it works. Yeah, actually, when we talked about the stopping protocol in gossip protocol, stopping condition for gossip protocol. Plain simply. Convergence. Okay. So yeah. All the known neighbors. Okay, if no new neighbors is the first one, tell everyone everything. But I guess all nodes don't know about each other in this. In Gossip Protocol, all nodes don't know about each other, but they have neighbors. So all nodes may not know about each other. So maybe H1 or HA only talks to B and C. Host A only talks to B and C as its replicated values. Host C only talks to A and D, and host B only talks to A and D. So it's still connected, but not all of them know about each other. So yeah, there's like some weird stopping conditions with the Gossip Protocol. So one is time to live. And what does that mean? It's each message carries a lifespan. So count hops. So max n hops. So that means you hop from one person to one person, one person, one person, one person to the other. And at some point you're like, okay, I've already hopped 3 times. Don't forward it anymore. Another one is threshold. Threshold based stopping. So I've heard this message 3 times already. I'm not going to propagate it anymore. Heard n times equal to stop propagating. Dude, I should make a systems design textbook. Not for learning systems design, but just for the interviews. Or maybe for learning systems design. Like, yo, these textbook writers, they got nothing, bro. I mean, they're okay. I read their textbooks, they're good. But I feel like people don't explain things in a simple enough way. Like, if it's not explained in a way that 3-year-old gets it, yo, it's too confusing. ChatGPT is good. Maybe I'll figure out a way to write a textbook with this. Easy after no has heard the same message in times. Nodes send and generate images, bro. It's so much easier to understand. Node send acknowledges back to the sender when a node receives enough confirmations. See, a lot of people, you don't even talk about what are the stopping conditions. Like that one guy's video, he just talked about, oh, you send to your neighbors. Bro, what's the stopping condition? You gotta ask the real questions. Okay, so third one is just acts, acknowledgements. Send acts to origin. It'll send act, maybe not to send. Stops gossiping. Oh, you send back to sender. Okay, yeah, again, just weird protocols. If you ask me what's the pros and cons of each of these, I could probably string up a solution, but acknowledgement based versus threshold based, it's if you ask me like when would you use threshold based instead of acknowledgement based, I have to think about it for a minute, you know? Good minutes. Distributed cache. What? What is the distributed cache for? So this is like S3. In-memory store Redis. Host 1. Okay, I actually want to see what he says to distributed cache, because that seems like a single point of failure. Oh, but it's distributed. So it's not. Okay, I actually want to see what he says.
But because about every other host in the cluster can share messages with each one, this host is used hard disk and hold. Another option is to resolve some user-provided information. For example, user specified ID. They include and expectable. Host will make question. Here's use this approach can scale out distributed implement. By the way, rating solution at Yahoo uses this approach. Next option is to use distributed cache cluster. For example, Redis. Or we can implement custom distributed cache solution. The pros for this approach is that distributed cache cluster is relatively small, and our service cluster can scale out independently. This cluster can be shared among many different service teams in the organization. or each team can set up their own. It is relatively tailored. Of course, in may require less messages to be broadcasted within the cluster, and one such option is to use a gossip protocol. This protocol is based on the way that epidemics spread. Computer systems typically implement this type of protocol with a form of random peer selection. With a given frequency, each machine picks another machine at random and shares data. By the way, rate limiting solution at Yahoo uses this approach. The next option is to use distributed cache cluster. For example, Reddit. Or we can implement custom distributed cache solution. The pros of this approach is that distributed cache cluster is relatively small, and our service cluster can scale out independently. This cluster can be shared among many different service teams in the organization, or each team can set up their own small cluster. Next approach also relies on a third-party component, a coordination service team. Next data is to use distributed cache cluster. For example, Redis. Or we can implement custom distributed cache solution. The pros of this approach is that distributed cache cluster is relatively small, and our service cluster.
Oh, I see. So this is just for broadcasting a message. So it'll send the message to distributed cache, and they'll send it to everybody else. Okay, that makes sense. That makes sense, man. That makes sense. So fourth is
can scale out independently. This cluster can be shared among many different service teams in the organization, or each team can set up their own small cluster. Next approach.
So hosts don't interact with themselves; they act through this proxy.
Also relies on a third-party
coordination service. Dude, honestly, I should become a tech YouTuber and explain stuff like onion routing protocol, how that works, using the onion routing protocol. Like, there's no good, I say, really good animation. Like, Fireship is pretty fire. That's good. Fireship, onion routing, but his videos are like more short form. Like, what was his recent video with, what's his face? Ross Ulbricht? Yeah, he made a good animation here to explain the onion routing protocol.
What you're looking at here is a 30 prison after receiving.
Let's see. Bro, but I think this guy realized, like, making educational content is not as good as making news content. People will watch the news every single day. People will not watch a video on how the onion routing protocol works. Yeah,
so only accessible.
So
like if you want your,
he explains how the DNS, he abstracts it too. He's not gonna go down into the dirty details about like DNS, how everything's an IP address, and how Fireship.io resolves to an IP address, how a website has multiple IP addresses, because it's not worth it for him, honestly. He does make those like really quick videos, which I like a lot, but I feel like he realized these are more value based, and those quick videos are really only for new services that people are interested in, because those are pretty value based too. But I think this guy's optimizing. He's not gonna make some long video on stuff that only a few people care about. How does this work? It routes it through multiple IPs to a hidden service. Tor relay. So you don't know the IP address of the end solution. It's encrypted both ways. Okay. I don't know. Yeah, I gotta watch the video on this, or just read something up. It's a layer above TCP or IP. It's a layer of whatever connection, above whatever connection you have. Wait, is Tor slow? Yeah. You can run your own relay? Dang. How can you make Tor faster? Bro, we can make the whole internet more secure if everybody got on Tor and started their own relay. So you're relaying information through your computer. And that would fix like the big brother attribute of Google, like knowing all your information. Like Google will sell your information to the cops pretty quickly. How many relays for Tor are there? Worldwide. How expensive is a relay to run? Can I run it on my Mac? Oh shit. Oh damn. Yeah, if you I remember watching like a Mr. Robot episode of this. If you run one of the start and relays, then you are kind of more risky because you know that there's some information from this IP going to the Tor network. So you know who's using the Tor network, but if it's a middle relay, there's more security because you don't know what the start IP or the end IP was. Is running a relay next to like real dangerous. I wouldn't just be able to see who's using end relay. Who's using the network, the Tor network. Exit relay. While it might seem like you could see who's on the Tor network more and legally sensitive, your relay is the last known Tor circuit, meaning that any traffic exiting the Tor network to access the internet will come from your IP address. Oh shoot. That's so bad. Can you see who's using your exit relay? Encryption, anonymity. But you gotta send it to somebody's IP if you're an exit relay. Oh, I guess when they say exit relay, they mean one of these exit relays. Oh yeah, because it goes through your IP and then it goes to a service. Oh, okay, so that's an exit relay. And what about entrance relays? Bum, bum. There's this one great YouTuber that I like to watch. Talks about a lot more niche stuff in the tech space. I don't know. You guys should watch it. Mental Outlaw. He's very big on just more the security aspects of certain things. Like, what's it? Like Tor network, Monero, all that good stuff. Bugs that come up, CVEs, which are critical vulnerability exceptions. Oh, yeah, Fad, you know CVEs? Damn straight. Critical vulnerability exploit. Okay, so one company I worked at, all I did was update libraries to avoid CVEs. It was the most brain dead work. Brain dead. The whole company was like, dude, we gotta fix all our CVEs. It was actually Autonomic, which was working for Ford. So this coordination service will be something like Zookeeper. And they're like, oh, dude, if we have an exploit and somebody makes all the Fords turn on at once or figure something out, then we'll be so screwed. So that was it. We were working on CVEs. The whole company was like, okay, I guess we're updating libraries across multiple services and monitoring services. That was it. So this one, you randomly select who the leader is and propagate. What's the difference between tell everyone everything and random leader selection?
Simplicity of the algorithm that has to be very reliable drawback is that we need to set up and maintain coordination service. Coordination service is typically a very sophisticated component that has to be very reliable and make sure one and only one leader is elected. But is this really a requirement for our system? Let's say we use a simple algorithm to elect a leader, but because of the simplicity of the algorithm, it may not guarantee one and only one leader, so that we may end up with multiple.
Ideally one.
multiple leaders being elected. Is this an issue? Actually, no. Each leader will calculate rate and share with everyone else. This will cause unnecessary messaging overhead, but each leader will have
Hi.
Each leader will have its own correct view of the overall rate. And to finish message broadcasting discussion, I want to talk about communication protocols, how hosts talk to each other. We have two options. If we're okay to have even less accurate solution, but the one that works faster, TCP should be our choice. Okay, we have implemented the algorithm.
TCP, slower but more security. UDP, less secure, but it's faster.
Created a set of classes and interfaces. Discussed message broadcasting. But how do we integrate all this code solution with the service? As we don't need to do any inter-process call. It's also resilient to the inter-process call failures, because there are no such calls. The second approach is programming language agnostic. It means that rate limiter daemon can be written on programming language that may be different from the language we.
Oh, what the hell? Everybody.
The first approach. It is faster, as we don't need to do any inter-process call. It seems tend to be very exceptional scenario.
Okay, faster, resilient to inter-process call failures. So whatever process we have the rate limiter. Otherwise, we interact with the rate limiter. Okay, makes sense. Makes sense. Let's see the end design, which was
On the service host, we have rules behavior that stores ETF rules in the local cache. When the request comes, a rate limiter client builds client identifier and passes it to the rate limiter to make a decision. Rate limiter communicates with the message broadcaster that talks to other hosts in the cluster. Let's recall non-functional requirements. Talk to other hosts in the cluster.
Okay, so each service host interacts with every other service host. Oh, do you know what ChatGPT is fire, bro? I wanted them to explain what the throttle rules cache is and the throttle rules retriever. Okay. Okay, so basically you can update rules on the fly. But you either cache the rules or retrieve them. So after some certain timeout, you should retrieve them. So you shouldn't be retrieving the rules every single time. That's kind of dumb. How often do the rules really change? Like every 24 hours? Where's ChatGPT? Okay, yeah, basically I'm pretty sure that's right. That's good enough. Now let's watch a video on TCP versus UDP. And let's make a little block here on message. Yo, is my battery low? No. Message broadcasting. We have well, let's just do one. Everything. We have the gossip protocol, which is and this could be related to forums actually. So this could be related to, this needs heartbeats from every node to every other node. This needs quorums. Yeah, gossip protocol is each other, so you need neighbors, not fully connected. Oh yeah, time to live for message hops. Threshold, scene X hops, or you could have ax, scene X ax of getting value, new value. Okay. Okay. Okay, what's the third one? Third one is distributed cache. What does this look like? Tell the cache what changed. Tell the other nodes to update. And then the cache tells the other nodes to update. Actually, how does this work? Yeah, I gotta use a washroom. How does this work for a messaging broadcasting? When data changes, cache system needs to ensure the node is in same sync, which apply to message broadcasting. Pub sub model. Okay. So everyone can publish and everyone subscribes. Gossip protocol, push-based notifications, polling. So lazy notifications. And it can get updates with pub sub. Eventual consistency with polling. What else is there? Eventual consistency with polling. Push-based notice. So push-based notice from cache or. Okay, we're gonna do the TCP UDP video later. I'm kind of tired. Poll-based polling, push-based gossip protocol. Yeah, or that doesn't make sense to have a gossip protocol there. Okay. What else? We had coordination service, like Zookeeper. So pick a leader. Leader handles message broadcasting to all other nodes. Followers. Zoo service holds record of all nodes via heartbeats. Okay. So you send an update to a node, it sends it to a coordination service. Okay, wait, explain this. Explain coordination service for message broadcasting. Okay. Helps manage and synchronize distribution. Sharing and distribution. Efficient routing, deduplication, avoiding bottlenecks, leader election, track state management, retrying if necessary. Okay. So let's just pick a leader. Track update has propagated. It checks. Distributed locks, prevent conflicts, membership tracking, failure detection, recovering. Okay, I think it's pretty good here. Last one was random leader selection. And the leader just propagates it. So yeah, you just kind of define a leader. Tell everyone everything. Everyone is treated as a leader. Why would we use a coordination service and elect a leader? A single leader. So why would you do this instead of and everything? I guess it's less complexity. Remove redundant messages, ensuring consistency, reducing coordination overhead. Yeah, so all nodes must continuously synchronize and check with each other. Failure recovery, high availability, avoid cascading failures. Okay, yeah, pretty good. Alright, I'm going to stream. See you guys. I'll start streaming again.